Now in this video we're going to look at two examples of applying the Mann-Whitney test. So this first example, which we'll call example 3.1, is a comparison of alloy strengths in steel cables. Now the data in the table below are the strengths of cables made from two different alloys, which we'll call alloy A and alloy B. The question of interest is whether or not there is a difference in location of the distribution of strengths of the two metal alloys. So you see we have our data set here, two samples, sample A and sample B, and the samples are independent of each other. So the null hypothesis will be that the two alloys are the same in terms of strength against the alternative that the two alloys differ in terms of strength. Okay, so we've already got the preliminary labeling in place as stated in the problem, and so now we need to come up with the labeling in terms of 1 and 2 based on the sample sizes. So there are 8 observations for alloy A and 10 observations for alloy B. So N sub A is 8, N sub B is 10, and because N sub A is less than or equal to N sub B, population 1 is going to represent the strengths of cables made from alloy A, and population 2 corresponds to the strengths of cables made from alloy B. So population 1 corresponds to population A, population 2 corresponds to population B. Sample 1, therefore, corresponds to sample A, and sample 2 corresponds to sample B. Alright, so now in terms of the labeling 1 and 2, so samples 1 and 2, populations 1 and 2, and so forth, we've got our notation here for the sample sizes. So N1 is equal to 8, N2 is equal to 10. We're going to specify rejection criteria using a significance level of alpha equal to 0.05. We're getting our critical point from table A10, and remember the critical points in A10 correspond to left-tailed tests for every type of test that we are going to perform using that table, and so the rejection criterion is going to be reject the null hypothesis if the test statistic T is less than or equal to some value. All tests using this table are left-tailed tests, and the inequalities are non-strict. So we have that less than or equal to, not the strict inequality, strictly less than. Okay, so here is the 5% table for table A10. So what we do first is look for the sample size corresponding to sample 1, so N1, right? So this is the column we're looking at. And then we look for the row corresponding to N sub 2. So I've got that highlighted here. And so we look for the intersection, and we see that the critical point for this test is 53. And so the rejection criterion at a 5% significance level is to reject the null hypothesis if the test statistic T is less than or equal to 53. To calculate the test statistic, we need to calculate T1, the rank sum for sample 1. We also need to calculate the conjugate of T1, so T1 prime. And the calculations are given here. I'll show you how we get these in a second. But T1, the rank sum for sample 1, is 106. To get the conjugate, we take N1 times the sum N1 plus N2 plus 1. So that's 19. So 8 times 19, and then we subtract off the value for T1. 8 times 19 is 152. We subtract off the 106. And so the conjugate to T1, T1 prime, is 46. Now, since this is a two-sided test, the test statistic, T, is given by the minimum of T1 and its conjugate. So it's the minimum of the 106 and the 46, and so the test statistic T is equal to 46. Now, how did we calculate this? Well, I implemented the procedure that was detailed in the notes, that multi-step process. The way I've done that in the context of a spreadsheet. All right, you might consider doing this as well. All right. So here I've got a portion of the spreadsheet that I use to calculate T1 and the conjugate of T1. So I've got a column here for the observation number, and these were not in the data set, but I'm just using these to keep track of which observation is which, to show some things later. All right, we've got 18 observations, and then I have a column for alloy, so alloy A or alloy B, and then corresponding to each observation and alloy, I have the measured strength. And so I've got those listed here. And notice that I've stacked the two data sets. I've stacked the two samples. So I can think of this as one big sample containing 18 observations. 8 observations from sample A, sample 1, and then 10 observations from sample B, which is sample 2 in this context. Ultimately, we need to rank these values. And to do this, we're going to create an ascending data array for this data set, for this combined sample. And we do this by sorting this spreadsheet according to this column C. And so that is shown in the next slide. So you can see here in this next screenshot of the spreadsheet, I've sorted the strength values in column C in ascending order. And now what we need to do, associated with each of these sorted observations, we need to give the rank. And the rank is going to correspond to the position within that ascending data array. Now we need to scan down here and look to see if there are any repeated values, because if there are repeated values, then we need to give the repeated values the arithmetic average of the positions that they have. And we don't see any repeated values here. So the ranks are just going to be simply the values 1 through 18. So you see that here. Now I've also got these 2 columns out here to the right, and these are labeled in terms of the labeling A and B. And so these are filled programmatically. I just have an if statement in this spreadsheet. If this rank here corresponds to alloy A, then it's going to put that value there. Otherwise, it will put it over in this column. So you can see here this alloy is B, so it's not going to put it in that column, it'll put it there. So it just does that automatically. Right, so I've got that programmed into the spreadsheet so that I don't have to manually do that, which would be a very, very tedious process. Now, once we have the ranks in the appropriate columns, so again, remember I talked about ranking the combined observations, but then separating those ranks out corresponding to their original samples. That's what I'm doing here. And so then all we need to do is calculate the column total for each of these last 2 columns, and that will give us the rank sum for sample A and the rank sum for sample B. All right, so down here, I've expanded the view of this spreadsheet, and you can see here that the sum of the ranks for sample A is 106. The sum of the ranks for sample B is 65. Now let me just say that if the null hypothesis were true, if there were no difference in the distribution of cable strengths, then the ranks would be pretty much evenly dispersed across the 2 samples. So these sums would tend to be fairly close if the null hypothesis were true. But if these 2 values are far apart, then that's an indication that the null hypothesis is not true. I'm also determining programmatically here in the spreadsheet the sample sizes for the 2 samples. So there are 8 observations in sample A and 10 observations in sample B. From those sample sizes, the sample size for sample A and the size of sample B, I am determining the sample sizes in terms of the 1-2 labeling, so sample 1 size and sample 2 size. So this is less than or equal to 10, so that's going to be sample 1 size N1, and N2 will be 10. And then because of that, T1, the rank sum for sample 1, is equal to the rank sum for sample A, because sample A is sample 1. So I'm just copying down this value, this 106, from that value right there. Once I have T1, I use the formula given in the previous lecture to calculate the conjugate of T1. So N1 times the quantity N1 plus N2 plus 1 minus T1. And so that is calculated programmatically. And so that is where we get that value. So T1 is 106. T1 prime, the conjugate of T1, is 46. And because this is a 2-sided test, the test statistic is the minimum of those 2 values. So it's the minimum of 106 and 46. And so the test statistic for our test is 46. All right, now remember the rejection criteria from table A10 was to reject the null hypothesis if the test statistic T is less than or equal to 53. And since our test statistic T is 46, the rejection criterion is satisfied, and so we reject the null hypothesis. And so we would say there is sufficient evidence at the 0.05 level of significance to conclude that a difference exists in the strengths of the cables made from the 2 alloys. So we're concluding that a difference does exist in the distribution of strengths of cables made from the 2 alloys. And based on the rank information given in this spreadsheet, for example, note that larger values numerically of the rank correspond to larger strength values. And so since sample A has the higher sum of ranks, we would conclude then that the difference exists and alloy A seems to be stronger. The next example is a taste test comparison of 2 types of hamburger substitute. So in a taste testing experiment, 2 types of hamburger substitutes, type A and type B, they were evaluated for quality of taste. 5 hamburgers using type A and 5 hamburgers of type B were ranked from best, which is 1, to worst, which is 10. So in this case, the ranking is opposite from the ranking in the previous example in terms of what's best and what's worst, but that's okay. So note in this experiment, ranks are not based on a quantitative measure, as was done in the previous example. Right? If you think back to the previous example, we had the strength measurements. Those values were measured on each cable sample, and then we ranked those quantitative values. But in this case, the ranks are not based on quantitative measures, but are obtained directly via the subjective assessment of the evaluator. So a person is ranking, they're not coming up with a quantitative measure which they then sort. They're just ranking the various samples based on their own subjective assessment. So the ranks are given in the table below. So we've got this table down here. For each sample, we have the type of hamburger substitute, whether it's A or B, and then we have the rank score assigned to it by the evaluator. So the question is there sufficient evidence at the 0.05 level of significance to conclude that the two types of burger substitutes differ in terms of their quality of taste? So the null hypothesis will be that the two types of hamburger substitute are the same in terms of quality of taste. The alternative will be that the two types of hamburger substitute differ in terms of quality of taste. Okay, so we've got the A and B labeling as given in the statement of the problem. Now we need to come up with the 1 and 2 labeling for analysis purposes. So the samples are each of size 5, so labeling, I'm saying here it's done arbitrarily, but the way I've got it set up in the previous notes, if n sub A is less than or equal to n sub B, then sample 1 corresponds to sample A. And that's actually what I'm implementing here. So let's label the data for type A as sample 1 and the data for type B as sample 2. So then n1 is equal to 5, n2 is equal to 5. We want to perform this test at the 0.05 level of significance. So we're going to again go to that first page in the table for A10. And from that table, okay, we're going to get a critical point. Regardless of the kind of test that we're performing here, when we're using table A10, we have a left-tailed rejection criteria. So we're going to reject the null hypothesis if the test statistic T is less than or equal to critical point obtained from table A10. All right, now we've got a sample size N1 of 5. This is the column we're looking at. And then sample size 2, n sub 2, is also 5. And so we see that the critical point for this test is 17. Okay, so the rejection criterion is to reject the null hypothesis if T is less than or equal to 17. All right, now it turns out, and we'll show the calculations in a moment, but it turns out that T1 is equal to 17. That's the rank sum for sample 1. The conjugate of T1 is 38. This is a two-sided test, and so the test statistic, T, is equal to the minimum of T1 and its conjugate, and so it's the minimum of 17 and 38, which is 17. All right, so how do we calculate this? Well, we carry out the procedure that was given in the last lecture, and again, I've implemented that in the context of a spreadsheet. You're free to do the same. You could program it in some other language if you want to, but I think that a spreadsheet is a good tool to use in this context. All right, so we start off with the data in the order in which it was presented in the spreadsheet. We've got the types here. And the way that the data were arranged in the original spreadsheet was according to the rank score that they were assigned by the evaluator. So there's not going to be much to do in calculating this or in processing the spreadsheet because this was already in order. So the ranks are just equal to those scores. Notice also that the cells for the columns TA and TB, again, are programmed to pick out the ranks for the appropriate samples. So this column, okay, these cells are programmed to pull out the ranks from this column for type A, and then the cells in this column are programmed to pull out the ranks for the type B values. All right, once we have that, we can calculate the column totals for those last two columns. And we see we have TA equal to 17 and TB equal to 38. The two sample sizes, NA is 5 and NB is 5. We then got these programmed down here to apply the rule that was given in the notes. So N1 is going to be equal to 5 in this case because that value is less than or equal to that value. And so N2 is equal to N sub B. T1, sample 1 corresponds to sample A, right? And so T1, the rank sum for sample 1 is equal to the rank sum for sample A, which is 17. And then remember that the conjugate of T1 is given by that formula. It's going to be N1 times the quantity N1 plus N2 plus 1 minus T1. So that is where we get that 38. Yeah, there's the calculation for that conjugate. N1 times 5 plus 5 plus 1, or 11, minus 17, which is 38. So since the test statistic, which is 17, is less than or equal to 17, we reject the null hypothesis. Now we're seeing right here why it's important to understand whether the rejection inequality is strict or not. Because this table is constructed to use non-strict inequalities, rejection inequalities, we are rejecting in this case. If the criterion was to use a strict inequality, then because 17 is not strictly less than 17, then we would not reject the null hypothesis. But in this case, we do use non-strict inequalities, and so we reject the null hypothesis here. And we can conclude then that there is sufficient evidence at the 0.05 level of significance to conclude that the two hamburger substitutes differ with respect to their quality of taste. And since hamburger substitute A had the more highly ranked scores, remember 1 meant best, 10 meant worst, we would conclude that type A is the better tasting hamburger. Alright, so that is the end of these two examples. We're going to see some additional information on how to test these hypotheses using large sample techniques, large sample approximations. And we'll see some more examples in the context of that information. All right, so I'll stop the video here and we'll continue on looking at large sample approximations to the Mann-Whitney test.